calculus for 5-4. 5-4 was talking about related rates, and we gave you these formulas. Some of them should have been memorized. Volume of a cube. Maybe not the surface area of a cylinder. Volume of a cylinder. But definitely the Pythagorean theorem and the area of a triangle. So what related rates is all about, and it's like geometry on steroids, right? So it's like, here's all these geometry formulas that we've always had, and now you have to imagine this dynamic nature where stuff is changing. Stuff is changing. So if I have this formula, y squared equals x squared minus z squared, I'm looking for the change in y, and they gave you all of these things. So if you're looking for the rate of change, that's the derivative. Rate of change is equal to the derivative. That's that instantaneous rate of change. At any minute that you tell me, freeze frame. Imagine something changing and you freeze. Okay, what's the rate that's changing at that minute? We spent all of September, October, November, December talking about the derivative is the instantaneous rate of change. You want the rate of change? I'm just going to take the derivative of it. So I take the derivative of my equation, and you can go ahead and simplify this. I divided everything by 2 just to keep it friendly. I circled what I was looking for, and after I circled what I was looking for, I just went ahead and plugged in what I knew. I knew how much my x was changing. I knew how much my y was changing. I'm sorry, Mr. Luke.
Right.
Do any of you have the calculators that came from that basket? Make sure you pass them up. He needs them for his geometry class. Yeah.
Can I get that someone?
Sorry about that.
No problem.
I forgot to bring them. Okay. 5-4 homework.
No, 5.
Oh, because you're leaving. Okay. Hold on just a minute. All right. So for this one, anyway, I plugged in what I knew, and I was able to solve for dy dt. Good luck. Number 2, if that's my area, find how fast the area is changing. What is the rate of change compared to time at that instant with each of those values? So once you take the derivative, you just plug in stuff in. Number 3, I love doing the drawings of these. We have our baseball player running. And each time I do this, something different's changing, potentially. So I need to make sure I read the problem carefully. He's running from first to second at a speed of 30 feet per second. So find the rate at which the distance from home plate, that's going to be my C, is changing. This is constant. This is going from 0 all the way up to 90. How fast is his distance changing? Because that is a constant, when I go ahead and I fill in the change of B compared to T, oh, no, A is a constant. See, that's where I get 0. This is where he's running at 30 feet per second. And that's how quickly my distance from home plate is changing. It's increasing at a rate of 16.64 feet per second. I needed to do a little Pythagoras over here to figure out at that moment what was C. If he's 30 feet from second base, that meant that this was 60, so he's actually a little further along than in my picture. Next up, my area of my rectangle is increasing 15 feet per minute. Notice my width and my length are changing at different rates. So I'm filling in, and my area is changing. So my change in my length with respect to time is 7/3 feet per minute. On the back, the base of a triangle is increasing. So my base is increasing at a rate of 0.4 centimeters per second, and my height is decreasing at a rate of 1/10 centimeters per second. So my triangle is being squished and spread out. When my height is 3 centimeters and my base is 10 centimeters, at what rate is the area increasing or decreasing? So I take my area formula, I take my derivative, I plug in what I know, and it turns out that my area is still increasing at that rate. A fish is being reeled in. Picture, I don't know, I guess I have a fishing rod that's 15 feet above. Here's my fish. He's very sad that he bit the hook. So he's being reeled in, and as he's being reeled in, this triangle is changing. I start with 25 feet of line. My 15 feet is a constant. So my sine is equal to my opposite over my hypotenuse. At what rate is the angle between the line and the water changing? In order to find the derivative, it's easier for me to write this as 15h to the negative 1, because that makes that easier. It doesn't specify, but rule of thumb, and this is hard for me in my geometry brain. In geometry, we're always talking about degrees, but you guys are talking about radians. So all this stuff is what's on the quiz. What I talk about now, not on the quiz. So today's lesson, and you can pack up all the cards. If anybody wants to borrow a pack of cards to go home, let me know and I'll loan them out to you. But you should have gotten, yeah, that's perfect. All right. So we're going to talk about optimization. So optimization is really basically why we have mathematics. Mathematicians care a lot about doing things as fast as we can. We want to optimize our efforts. We want to make sure that we're getting the most out of whatever we can. So the definition of the word optimize is to make the best or most efficient use of a situation or resources. Sometimes we want to maximize our space. Sometimes we want to minimize something like our cost. So when we're talking about optimizing, it can be a conversation either thinking by finding our maximum or our minimum. Now that we kind of have that in our head, if I'm talking about a graph and I'm looking to maximize my graph, I want to find where that vertex, that high point is, or that low point, that local minimum or maximum. Of course, that's going to be where my derivative or my slope of my tangent line is 0. So we'll think about that as we move through. All right, so how do we use calculus to maximize? In mathematics, to optimize means to maximize or minimize something. So when we look at this function, what are my maximums or minimums of the function? Talk to your group mates. and agree on maximums and minimums. Go. All right, so if I have my slope of my tangent line, when I'm talking about a minimum, I know that that's right here. What's true about this tangent line and its slope at the minimum? What's true? Yeah. So when my tangent line, when my slope on my tangent line, that's going to be the very minimum of what I'm talking about. So if I'm talking about my minimum, I'm talking about the slope of my tangent line equaling 0. That's when I'm looking at my derivative. So as my tangent line progresses, I'm going up, 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 and then I'm looking at my tangent line. Here is going to be the slope of my tangent line. At the maximum of my graph, I again have a slope equals 0. So in Algebra 2, when you spend all that time finding your local minimums and your local maximums, remember that? Your local max and your local minimums. We talked about hills and valleys. We're talking about, we want to know those places where my slope of my tangent line is 0. So where my derivative is equal to 0. So what do we know about the function at these points? We have some conversations that we can talk about what's true about the function at these points. At each of these points, I go from having a positive to a negative slope. So I have a change in my sign of my slope of my tangent. So I know that at the maximum or the minimum, that derivative is going to be equal to 0. We define a minimum as the lowest point with 2 points on either side. The maximum is the high point with 2 points over side. So if you can picture that change in the slope of that tangent line, whenever that slope goes from being positive to negative or negative to positive, it crosses 0. So that's going to be where that happens. All right, so our guidelines for solving problems is we're going to draw a picture if we can, because the pictures help us see things. We're going to identify any known or unknown quantities. We're going to write an equation that needs to be optimized, and then we're going to rewrite the equation in terms of one variable. This becomes super important because when we go to figure out that optimization, we're only looking for one derivative at a time, one rate of change. We're going to optimize by finding our maximum and minimums, take that derivative and set it equal to 0. All right, so on the back we have a couple examples here. Find two numbers whose sum is 30 and whose product is as large as possible. So what are we looking for, a minimum or a maximum here? We're looking for a maximum. So if I let x equal my first number and y equal my second number, with your group, talk about an equation that you could write to represent the story of the problem. Once I define my variables and I write my equations, Now what I want to do is try to substitute one variable for the other. So I'm going to go ahead and say that x is equal to 30 minus y. So then I can say that 30 minus y times y is equal to p. I can say that 30y minus y squared is equal to p. And now what I have is one equation that relates both of my variables. And now I can find the derivative. So what I want to do here is this equation is going to relate. And then what I want to find is when the derivative of this equation is equal to, if I want to find my maximum product, right? Find two numbers whose sum is 30 and whose product is as large as possible. Does that make sense to you? Right? So if I want to maximize the product, I want to figure out when my derivative is equal to 0. So we can take the derivative, and I can say 30 minus 2y dy. Well, we don't have to do this because it's not in terms of t. So dy dy is equal to dp dy. And that relates my two variables. Let's take a look at example 2. Find the length and width of a rectangle that has a perimeter of 100 feet and the maximum area. So if my length and my width, the formula for my area, the formula for my perimeter, so find the length and width of a rectangle that has a perimeter of 100 feet and has the maximum area. Talk to your group mates about what you're going to substitute in for what. Here's our area equation. Here's our perimeter equation. I went ahead and I solved for L in terms of W. I put W in. Simplify. I found a change in my area with respect to my width. And I was able to do this, that's why I don't have to worry about that other rate. There's no dW per dW. I only have one rate that I'm looking for, and I want to know, when is this derivative 0? So I put 0 in. If my width is 25, I plug back in here, my length is 25, and that's where I maximize my area. Let's go back up to our first problem. 30 minus 2y, I plug 0 in. 30 is equal to 2y. So my largest product happens when y is equal to 15. And therefore, x is going to be also equal to 15. Interesting conversation about their largest product. The largest area happens when these are the same length and width. We're going to talk about that next class after your quiz. Do an activity that has to do with that. All right, example 3, you're creating an open top box with a piece of cardboard that's 16 by 30 inches. So we'll make it 16 a little smaller than that. So we have a 16-inch and a 30-inch box. I'm going to snip rectangles or squares out of the corners of my rectangle. I'm creating an open top box with a piece of cardboard. So what I'm going to do is I'm going to fold each of these sides up. Because I'm going to cut out. I'm going to cut out a little square here, cut out a little square here, and here, and here. What size square should be cut out of each corner to create a box with the largest volume? So what I'm going to end up with is a box that looks like this. My volume is equal to my length times my width times my height. There's a problem. I need to figure out a way to represent all of this in terms of one variable. My height here is x because that's what's cut out. What would you say my length of my box is? 30. But I don't have this in here. 30 what? Yep. What would you say my width is? What would you say my width is? Yeah. So we can simplify this in stages. Volume is equal to 30 minus 2x. We can call this 16x minus 2x squared. And then you can FOIL that together. Take a minute and do that with your group mates. So I'll go ahead and I'll differentiate that. And I'll say that dv dx is equal to x squared minus 24x plus 120. Set that equal to 0. Yeah.
Oh, why do you have 2x? Minus 2x.
Because this length originally was 30, but I lost an x here and I lost an x here. So whatever x is worth, I'm losing twice that on my length. And the same thing happened with my width. I had 16 and I lost an x here and I lost an x here. Yeah.
And wouldn't it be 3x squared? So 2 squared? I mean,
So what I did first when I multiplied, when I multiplied these three things together, I just distributed this x first, and then I FOILed these.
oh yeah, I'm talking about the derivative in the bottom that you just did. Maybe 3x.
Oh, yeah, no, it should be,
So it came from x.
yeah, 3x squared. So this should be 3x squared. That makes more sense. Minus 24x plus 120. You can put a Smarty up. I don't think that factors, does it? $40 is 4 and 10, 2 and 20, 8 and 5, right? So we'll go ahead and say that A is equal to 1, B is negative 8, C is equal to 40. X is equal to the opposite of B plus or minus the square root B squared minus 4. Uh-oh, I'm going to get a negative number. All right, where'd I mess up? My volume is length times width times height. 30 minus 2x, 16 minus 2x times x is length times width times height. Sixteen times 30, 480. First terms. Inside terms. First terms. Inside. Oh, this shouldn't be 16. This should be 6D. Right? First, here's my inner. My outer is minus 60. X squared plus 4x cubed. Right? 4x cubed. 32 and 60. What's that? 92? (92x squared). If I divided that by 4, that brings us down to 23. Because I can't have a negative number under here. That's how I knew I screwed up. So 3x squared minus, now it's 23. X's, no, Because 2 times 23 is 46, right? Plus 120. I can't divide by 3 anymore, so I'm going to have to change all my... So this is going to stay 3x squared. This stays 46x. And this stays 120. So my A is 3. My B is negative 46. My C is 120. So quadratic formula has x is equal to the opposite of b, which is 46 plus or minus the square root of b squared, which is 2,116 minus 4 times a times c. That's better. I don't get a negative number. All over 2a. So my x is equal to 46 plus or minus the square root of 676. That's perfect square, y'all. 46 plus or minus 26 over 6. X is equal to 12. And 3 1/3, which is 10/3. The quadratic formula. Woo. Okay, so what did we solve for? Making our volume as big as it could be. Making our x either 3 1/3 or 12. Either one of those sound ridiculous to you? Either one of those sound ridiculous? 12 doesn't sound ridiculous? It should sound ridiculous. Because if I only have 16 inches and I have to subtract 12 twice, I'm a little short. Right? Can I subtract 12 twice? Remember, here's an x and there's an x. Can I subtract 12 twice? No. So this is what we call that extraneous solution. So your answer here all right, let's set up this first one. If I have f of x equals x squared, that's this parabola that sits lovely right at the origin like that. If I have a point on the graph 2 1/2, I want to find the point on the graph that is closest to this. I want to optimize and have the minimum distance. I want to find the point on the graph where x squared is closest. Now keep in mind, I could measure this way, I could measure this way, but what I want is to find this xy ordered pair where that distance is minimized. Your distance is equal to the square root of the change in your x's squared plus the change in your y's squared. It might be easier to rewrite your radical like that. We have too many x's and y's. Let's fill in what we know. This x we know is worth 2, and this y we know is worth 1/2. How do I know that? It's given. That still leaves me with an x and a y. Is there a way I can use this to express it? What is my equation? So my new x value minus my old one squared plus my new y value minus my old one squared, all to the, let's talk about what I did. If I put this x into this function, what is my output? I'm going to have to get another piece of paper for this one because we're totally talking chain rule, right? Because when we take the derivative of this, I want to maximize my distance, right? Or minimize my distance. So we'll have to do the chain rule. Very fun. All right, so here's your homework. For those of you who have been taking it easy and not doing calculus on a regular basis, welcome back to calculus. Welcome back to school. Welcome back to college level math class. For those of you who haven't been watching the videos, doing the homework, asking questions when you don't understand, welcome back. You need to be doing some calculus. We'll finish this one and I'll share the answers when you get back. When I see you next week.